Hello, and welcome to my Chanel. I'm truly glad you found your way here. The world outside can be restless, noisy, and fast, but here, things soften and slow. This is a quiet place where curious minds can drift gently toward sleep, or simply wander through ideas while resting. Tonight, we're not only talking about neurons, brain scans, or electrical signals. We're stepping into the mind itself, into that strange and luminous inner space where thoughts take shape, memories begin to stir, and the feeling of being you quietly comes alive. Tonight, we'll explore 100 fascinating facts about consciousness. We'll move from the brain's hidden mechanisms to extraordinary cases that challenge much of what we think we understand. Some of what you hear may feel familiar. Some of it may be so unexpected that it lingers with you long after morning comes. And before we begin, if these calm and curious journeys help you unwind, relax, or gently close your day, consider liking, subscribing, or sharing your thoughts below. It helps other sleepy souls find their way here too, one quiet evening at a time. Now, if you're ready, let's begin. Scientists still cannot agree on one single definition of consciousness. Ask 10 experts what consciousness really is, and you may hear 10 very different answers. Some define it simply as awareness of the world around you and of your own inner thoughts. Others describe it as a layered process involving perception, self-reflection, memory, and the ability to imagine what has not happened yet. Philosophers, neuroscientists, and psychologists often approach the topic from completely different directions, using different language to describe what may or may not be the same phenomenon. Even the question of whether animals, machines, or newborn infants are conscious can trigger intense debate. This lack of agreement makes consciousness especially difficult to study. It is not easy to measure something when people cannot even fully agree on what it is. Despite advances in brain imaging and computing power, no single theory has united the field. For now, consciousness remains one of the most intriguing puzzles in science, and perhaps the most personal mystery any of us can explore. Your brain generates enough electrical activity to power a small light bulb. The human brain runs on electricity, not in the same way as a household machine, but through electrochemical signals carried by billions of neurons. Each neuron creates tiny changes in voltage as ions move in and out of the cell, producing the brain's characteristic electrical patterns. Altogether, this activity generates about 20 watts of power, enough to light a small bulb. What makes this so remarkable is how much the brain achieves with such modest energy. That quiet electrical output coordinates every thought, every movement, every sensation, and every emotion. Even while you sleep, the brain never truly shuts down. It continues regulating essential bodily functions and processing memories in the background. Modern computers often require far more power to perform tasks much simpler than what your brain can do in a fraction of a second. It is a striking reminder of both the efficiency and the mystery of the biological machinery that supports your conscious life. Consciousness can return in the middle of surgery if anesthesia fails. For most people, general anesthesia feels like slipping instantly into darkness and then waking up later with no memory of the time in between. But in rare situations, anesthesia awareness can occur. When a patient regains consciousness during surgery, the experience may range from a vague awareness of voices or pressure to, in the most distressing cases, feeling pain while being unable to move or speak because of muscle relaxants. Researchers estimate that this happens in roughly 1 to 2 cases per 1,000 surgeries involving general anesthesia. Factors such as underdosing, unusual metabolism, or high resistance to anesthetic drugs can increase the risk. Modern monitoring techniques have lowered the chances significantly, but no method is perfect. This phenomenon is unsettling not only for patients, but also for anesthesiologists, because it reveals how much remains unknown about the exact mechanisms of consciousness and how to reliably switch it off and back on again. The brain can remain aware for a few seconds after the heart stops. When the heart stops pumping blood, consciousness does not necessarily vanish at once. Studies of cardiac arrest patients have shown that brain activity can continue for several seconds and sometimes longer after circulation ceases. In some cases, survivors of near-death experiences have reported vivid perceptions and memories during this brief interval, even describing events that took place while they were clinically dead. Scientists believe this lingering awareness may happen because the brain is using its last remaining reserves of oxygen and glucose before shutting down. These final bursts of organized neural activity may produce unusual sensations, such as tunnels of light, strange calmness, or heightened clarity. While this does not prove that consciousness survives death, it does suggest that losing awareness may be a more gradual process than we often assume, and that the brain's final moments may be much more complex than a simple on and off switch. Some coma patients can communicate using brain scans alone. A coma is usually imagined as total unconsciousness, but advanced imaging has shown that some patients diagnosed as unresponsive may still retain islands of awareness. In specialized experiments, researchers have asked these patients to imagine playing tennis or walking through their home. Each of those mental tasks produces a distinct pattern of brain activity that can be detected by functional MRI. By assigning yes or no answers to different imagery tasks, some patients have successfully communicated without moving or speaking at all. This discovery has profound implications for diagnosis and care. It offers families a possible way to connect and gives patients a voice when their bodies cannot respond. It also forces scientists to rethink what it really means to be conscious and reminds us that the boundary between awareness and unawareness may be far thinner than traditional bedside tests once suggested. Blindsight allows people to detect objects they cannot consciously see. Blindsight is a rare and fascinating condition in which people with damage to the primary visual cortex lose the ability to consciously see, yet can still respond to visual information. For example, a person with blind sight may correctly guess where an object is located or detect its movement, even while reporting total blindness in that part of the visual field. Scientists believe this happens because visual signals can travel along alternative neural pathways that bypass the damaged region, reaching areas of the brain that guide movement and orientation without creating conscious vision. Blind sight challenges the assumption that perception and awareness are always inseparable. It shows that the brain can process surprisingly complex information without that information ever entering the bright center of conscious experience. Split brain surgery can create two separate streams of awareness. Split brain surgery, once performed to treat severe epilepsy, involves severing the corpus callosum, the thick bundle of nerve fibers connecting the brain's two hemispheres. Patients who undergo this procedure can still function normally in most everyday situations. But laboratory tests reveal something extraordinary. Each hemisphere can process information independently. For instance, if an image is shown only to the right hemisphere, which controls the left hand but not speech, the patient may be unable to name the object, yet still draw it accurately with the left hand. This suggests that each hemisphere may hold its own separate version of awareness. The phenomenon raises deep and unsettling questions. Are there now two minds sharing one body? Or does consciousness somehow remain unified, even after the bridge between the hemispheres has been divided? Certain drugs can erase memories without affecting intelligence. Some medications, especially those in the sedative and anesthetic families, can interfere with the brain's ability to form new memories while leaving other mental functions largely intact. Midazolam, for example, can make a person appear alert and conversational during a medical procedure, yet afterward they may remember nothing about the experience at all. This effect, called anterograde amnesia, targets the hippocampus, a region essential for converting short-term memories into long-term storage. While this property can be medically useful, especially for reducing distress during surgery or painful procedures, it also reveals something important. Memory and consciousness, though closely connected, are not the same thing. You can be completely aware in the moment, yet later lose all trace that the moment ever happened. Some people experience a complete loss of self during meditation. Certain advanced meditation practices, especially during long retreats or deep states of concentration, can produce what practitioners describe as ego dissolution, a temporary disappearance of the sense of being a separate self. In these moments, perception may feel vast, open, and unbounded. Thoughts may slow dramatically or stop altogether, and the line between self and world may blur or disappear. Brain scans of experienced meditators show altered activity in regions associated with self-referential processing, including the default mode network. While many describe the experience as peaceful, freeing, or deeply profound, it can also feel disorienting to someone who is unprepared for it. Studying these altered states gives researchers a rare glimpse into how fluid and flexible our sense of identity may actually be. The locked-in state traps a fully conscious mind inside a paralyzed body. Locked-in syndrome is a rare condition, often caused by damage to the brainstem, in which a person loses nearly all voluntary muscle control while remaining fully conscious and aware. Most cannot speak, move, or even blink, though some retain limited eye movement. In such cases, communication becomes possible only through painstaking eye-tracking systems or blinking responses to yes or no questions. Despite the severity of the condition, personality and cognitive ability often remain intact. For the person inside, it can feel like being imprisoned within a motionless body, a complete separation between mind and movement. This condition highlights the difference between consciousness itself and the ability to express it, and explains why modern neuroscience increasingly depends on technology to detect awareness when no outward signs are visible. People can perform complex actions while asleep, including driving. Sleepwalking is a type of parasomnia in which the brain enters a mixed state somewhere between sleep and wakefulness. Most episodes involve simple actions, such as walking around the house or rearranging objects. But in rare cases, people have cooked meals, left their homes, and even driven cars while still technically asleep. During these episodes, the brain's motor systems remain active, but higher reasoning and memory formation are largely offline. That is why sleepwalkers often remember nothing afterward. This phenomenon shows that not all movement and not all behavior requires full conscious awareness. Complex routines can sometimes unfold almost entirely through automatic processes. Fascinating as it is, sleepwalking can also be dangerous, especially when a person encounters hazards in the environment without the judgment that comes from being fully awake. Sleep paralysis leaves you awake but unable to move. Sleep paralysis happens when the mind wakes up while the body is still in atonia, the natural paralysis that prevents you from acting out your dreams. People experiencing it find themselves fully conscious, able to see and hear, yet completely unable to move or speak. The episode may last from a few seconds to several minutes, and it is often accompanied by vivid hallucinations, such as sensing a presence in the room or seeing shadowy figures nearby. These sensations are thought to be fragments of dream imagery bleeding into wakefulness, amplified by the brain's fear response. Sleep paralysis is not dangerous in itself, but its intensity can feel deeply unsettling. Understanding it as a temporary mismatch between brain and body states can help reduce fear. Even so, in the moment, the vulnerability can feel overwhelming. Our sense of time can slow dramatically during life-threatening events. Many people who have experienced accidents, sudden falls, or other moments of extreme danger describe the event as unfolding in slow motion. Scientists believe this sensation is linked to the brain's heightened attention and memory processing during stressful situations. When danger appears, the amygdala, a brain region involved in emotional responses, signals other parts of the brain to record far more detail than usual. Because the brain is capturing so much information in such a short period, the memory later feels stretched out in time. When people recall the event afterward, the abundance of stored detail creates the impression that the moment lasted longer than it actually did. In reality, reaction speed does not necessarily increase. Instead, the brain is packing more information into each fraction of a second. This distortion of time perception can be helpful for survival, allowing a person to focus intensely on critical details. It also shows how flexible and subjective our sense of time can be under different states of consciousness. Psychedelic substances can temporarily dissolve the sense of self. Compounds such as LSD, psilocybin, and DMT can produce a state often described as ego dissolution. In this condition, the usual boundaries between self and environment begin to fade or disappear. Many people report a powerful feeling of unity with the world around them, as if the idea of I has been replaced by a broader awareness that includes everything. Brain imaging studies suggest that psychedelic substances reduce activity in the default mode network, a group of brain regions associated with self-referential thinking and personal identity. When this network becomes quieter, the mind may loosen its attachment to the personal story that normally defines the self. For some people, the experience feels peaceful, insightful, or even transformative. For others, it can feel confusing or overwhelming. Scientists continue to study these altered states because they offer valuable clues about how the brain constructs our sense of identity. Some brains are capable of rewiring themselves after massive injury. This ability is known as neuroplasticity. Neuroplasticity refers to the brain's capacity to reorganize its structure by forming new neural connections. After events such as strokes, traumatic injuries, or surgical removal of brain tissue, surviving regions of the brain can sometimes take over tasks that were once handled by damaged areas. This rewiring may occur gradually through therapy and repeated practice, or sometimes through spontaneous adaptation. For instance, if one section of the motor cortex is injured, nearby neurons may slowly learn to control the affected muscles. In cases where language ability is lost, other parts of the brain can sometimes develop alternative pathways for speech. Recovery depends on many factors, including age, health, and rehabilitation. Even so, neuroplasticity shows that the brain is far more adaptable than scientists once believed. This capacity for adjustment helps explain how consciousness can continue despite significant physical damage to the brain. Brain injuries can sometimes change a person's personality almost overnight. Certain types of damage do not merely affect memory or movement. They can transform personality so deeply that friends and family feel they are interacting with a different person entirely. One of the most well-known historical cases involved Phineas Gage, a railroad worker in the 19th century who survived an iron rod passing through his skull. Although he retained his intelligence and basic abilities, those who knew him reported dramatic changes in his behavior. He became impulsive, irritable, and unreliable. Injuries affecting the frontal lobes, especially the prefrontal cortex, can disrupt emotional regulation, decision-making, and social behavior. These changes reveal something profound. Our personality, something we often think of as fixed and deeply personal, is closely connected to physical brain structures and chemistry. Identity and consciousness are not separate from the brain, they are built upon it. Phantom limb sensations can make the mind feel body parts that are no longer there. After an amputation, many people continue to feel sensations in the missing limb. In some cases, they even experience pain in a hand or leg that no longer exists. This phenomenon is known as phantom limb syndrome. It occurs because the brain's internal map of the body does not instantly update when a limb is lost. Neurons in the somatosensory cortex, the brain region that processes touch and movement, may still become activated by signals from neighboring areas. As a result, the brain generates the sensation that the limb is still present. Some people feel itching, pressure, or movement in the phantom limb. In certain cases, the sensations are so vivid that individuals instinctively try to move or scratch it. Treatments such as mirror therapy use visual feedback to help retrain the brain and reduce discomfort. Phantom limbs reveal that our experience of the body is largely constructed inside the brain, and can persist even when physical reality changes. Some blind individuals learn to perceive their surroundings through sound. Certain blind people develop a form of human echolocation. They create clicking sounds with their mouths or tap a cane against the ground, then listen carefully to the echoes that bounce back from nearby surfaces. With enough practice, these echoes allow them to estimate distance, recognize shapes, and detect obstacles. Brain imaging has shown that skilled echolocators activate parts of the visual cortex while interpreting these sounds, even though those areas normally process visual information. In other words, the brain repurposes regions that would otherwise remain unused. Although echolocation does not replace vision in the traditional sense, it provides a remarkable level of spatial awareness. This adaptation highlights the brain's ability to reorganize itself and develop new ways of interacting with the world. The brain can create vivid hallucinations in total silence and darkness. When people are deprived of sensory input for long periods, such as in dark and silent environments, the brain often begins producing its own sensations. Individuals in sensory deprivation settings may see shifting lights, hear phantom sounds, or experience elaborate visual scenes. These hallucinations occur because the brain constantly predicts and fills in sensory information. When real input disappears, those predictions can grow increasingly vivid. Short periods of sensory isolation can feel relaxing and even meditative. However, extended deprivation may become disorienting or unsettling. This response demonstrates that conscious perception is not simply a passive recording of the outside world. Instead, the brain actively constructs much of what we experience. Lucid dreamers can communicate with scientists while asleep. Lucid dreaming occurs when a person becomes aware that they are dreaming and may even gain some control over the dream. In recent experiments, researchers discovered ways to communicate with lucid dreamers during sleep. Participants were instructed to respond to yes or no questions by moving their eyes in specific patterns or making subtle facial movements while in REM sleep. Because these signals can be measured in sleep laboratories, scientists were able to receive real-time responses from people who were still dreaming. This discovery demonstrates that awareness is not limited to waking life. Even during dreams, part of the mind can remain connected to the outside world. Consciousness can disappear temporarily during certain epileptic seizures. Not all seizures involve dramatic physical convulsions. Some types, such as absence seizures or complex partial seizures, can briefly interrupt conscious awareness while the body remains mostly still. From the outside, it may appear that the person has simply paused mid-sentence or is staring blankly into space. Internally, however, there is often no memory of the episode at all. These events may last only a few seconds, but completely remove conscious experience during that time. Brain recordings reveal sudden waves of synchronized electrical activity spreading through neural networks, disrupting the normal patterns required for awareness. After the episode ends, the person may continue speaking or moving as if nothing happened, unaware that time briefly vanished. Deep brain stimulation can influence consciousness directly. Deep brain stimulation, often abbreviated as DBS, involves implanting electrodes into specific regions of the brain to deliver controlled electrical pulses. This technique was originally developed to treat movement disorders, such as Parkinson's disease. However, It has also produced surprising effects related to consciousness. In rare cases, stimulating the thalamus, a central relay station for sensory information, has restored awareness in patients who were previously in minimally conscious states. In other situations, stimulation of certain regions can temporarily disrupt awareness, almost like flipping a switch. These findings suggest that consciousness relies on a delicate balance of activity across interconnected neural networks. By adjusting that balance electrically, scientists can sometimes alter a person's state of awareness. Narcolepsy can cause people to fall directly into dream sleep. Narcolepsy is a neurological disorder that disrupts the brain's regulation of sleep and wakefulness. One of its most striking symptoms is cataplexy, a sudden loss of muscle strength triggered by strong emotions such as laughter or surprise. In some cases, individuals with narcolepsy transition directly from wakefulness into REM sleep without passing through the usual intermediate stages. Because the body becomes naturally paralyzed during REM sleep to prevent acting out dreams, this sudden transition can cause a person to collapse unexpectedly. During cataplexy, the individual remains conscious but temporarily unable to move. In narcoleptic sleep attacks, however, awareness may quickly give way to vivid dream imagery. Studying narcolepsy has helped researchers understand how the brain shifts between different states of consciousness and how those transitions can sometimes malfunction. In rare cases, people can hear colors or taste shapes. This unusual experience is known as synesthesia. Synesthesia is a neurological condition in which stimulation of one sense automatically triggers sensations in another. The most common form involves seeing colors when hearing sounds, or associating letters and numbers with particular hues. But some versions are far more unusual. A person might taste flavors when touching certain textures, or hear distinct tones when looking at bright colors. Brain imaging studies suggest that people with synesthesia have stronger connections between sensory regions of the brain, allowing signals to cross between areas that are normally separate. For those who experience it, synesthesia is not random. The same sound always produces the same color, the same shape, or the same taste. While many synesthetes describe the experience as enriching and vivid, it also raises deeper questions about perception. It reminds scientists that the way we experience reality is partly constructed by the unique wiring of each individual brain. Some people possess memories so vivid that they can recall almost any day of their lives. A small number of individuals have what scientists call highly superior autobiographical memory, or HSAM. People with this ability can recall events from nearly any date in their lives with astonishing detail. If asked about a random day from many years ago, they may describe the weather, the clothing they wore, the conversations they had, and what happened in the news that day. Their recollections can be so precise that they often rival written diaries. Brain scans of individuals with HSAM show subtle differences in regions involved in memory storage and retrieval, yet the exact biological cause remains unclear. Although this ability might sound like a gift, many people with HSAM say it can also feel overwhelming. Painful or embarrassing memories can remain just as vivid as joyful ones. Their experience offers scientists a living example of how memory and consciousness are deeply intertwined. Hypnosis can reduce or even block pain without medication. Hypnosis is a state of focused attention combined with heightened responsiveness to suggestion. When guided by a trained practitioner, a person in hypnosis may become deeply relaxed and highly attentive to particular mental images or ideas. In medical settings, hypnosis has sometimes been used to help patients undergo dental procedures, minor surgeries, or childbirth with significantly reduced pain. Under hypnosis, suggestions can alter how the brain interprets pain signals, making them feel distant, dull, or even absent. Brain imaging studies reveal that hypnosis can modify activity in regions involved in both the sensory and emotional aspects of pain. Not everyone responds equally to hypnosis, but for those who do, the effect can be remarkable. These findings demonstrate that conscious perception of pain is not fixed. Instead, the brain can reshape its experience of discomfort through attention, expectation, and belief. Placebo effects can trigger measurable healing responses in the brain and body. The placebo effect occurs when a person's symptoms improve after receiving a treatment with no active medical ingredient, simply because they believe it will help. Far from being imaginary, placebo responses involve real physiological changes. Brain scans show that when someone expects relief, the brain can release natural pain-relieving chemicals similar to opioids. Placebo responses have been observed in conditions ranging from chronic pain to depression and Parkinson's disease. By activating the brain's own regulatory systems, belief alone can influence both perception and physical health. Although placebo treatments are not substitutes for proven medical therapies, they reveal how strongly expectations and conscious beliefs shape our experiences. Understanding this effect may eventually help researchers design treatments that better harness the brain's natural healing mechanisms. Biofeedback training allows people to influence bodily functions usually considered automatic. Biofeedback uses sensors that provide real-time information about physiological processes such as heart rate, muscle tension, skin temperature, or breathing patterns. By observing this feedback and practicing techniques like controlled breathing or focused relaxation, individuals can gradually learn to influence these functions consciously. With enough training, people can reduce stress responses, manage chronic pain, and even improve certain aspects of athletic performance. Some advanced practitioners can warm their hands by several degrees or slow their heart rate significantly through mental focus alone. Biofeedback shows that the boundary between voluntary and involuntary control in the body is more flexible than it might seem. With the right tools and awareness, conscious attention can reach deeper into bodily processes than most people realize. Extended isolation can cause the mind to lose its sense of time. When people are cut off from environmental cues such as daylight, clocks, and social interaction, their internal sense of time can quickly begin to drift. In experiments where volunteers lived in underground bunkers or isolated environments for weeks or months, many participants lost track of normal day-night cycles. Some began living according to internal days that lasted much longer or shorter than 24 hours. Others reported feeling as though only a few days had passed when several weeks had actually gone by. The brain relies heavily on environmental signals to keep its internal clock aligned with the outside world. Without those signals, consciousness can begin following its own rhythm. These findings have important implications for astronauts, submarine crews, and anyone who spends long periods in closed or artificial environments. Some people form extremely convincing memories of events that never happened. These are known as false memories. A false memory is a recollection that feels vivid and real, but is either entirely fabricated or significantly distorted. The brain naturally fills in missing details when recalling past events, which makes memory flexible but also vulnerable to error. In psychological experiments, participants have sometimes been persuaded to remember entire fictional childhood events, such as being lost in a shopping mall, simply through repeated suggestion. Brain imaging studies show that recalling a false memory activates many of the same neural systems involved in remembering real events. This means that from the brain's perspective, the difference between real and imagined memories can become blurred. These discoveries demonstrate that conscious memory is not a perfect recording of the past. Instead, it is a constantly reconstructed story shaped by experience, suggestion, and imagination. Consciousness may depend more on brain connectivity than on brain size alone. Large brains do not necessarily guarantee more complex consciousness. Animals such as whales and elephants possess brains larger than those of humans. Yet human brains contain extremely dense networks of neural connections that allow information to move quickly between different regions. It appears that the organization and efficiency of these networks may be more important than sheer size. Rapid communication between brain regions allows sensory information, memories, and decisions to integrate into a unified experience of the world. In contrast, a larger brain with fewer efficient connections may not perform certain cognitive tasks as effectively. This is one reason why some birds and primates with relatively small brains demonstrate impressive problem-solving abilities. Their neural wiring is remarkably efficient. The smallest brains capable of complex behavior may belong to insects. Honeybees, for example, possess brains containing fewer than 1 million neurons. Compared to the billions of neurons in the human brain, this number is tiny. Yet bees display surprisingly sophisticated behaviors. They can navigate long distances, recognize patterns, remember food locations, and communicate through intricate waggle dances that convey direction and distance to other bees. In laboratory experiments, bees have even demonstrated the ability to distinguish abstract concepts such as same and different. While scientists continue to debate whether insects possess any form of consciousness, their abilities go far beyond simple reflex behavior. Studying these tiny brains helps researchers understand how relatively small neural systems can still integrate information, make decisions, and adapt to changing environments. Octopuses distribute much of their intelligence throughout their arms. Unlike humans, octopuses do not concentrate most of their nervous system inside their heads. Roughly 2/3 of an octopus's neurons are located within its arms. Each arm has the ability to sense, taste, and coordinate movements independently of the central brain. In experiments, detached octopus arms have even been observed responding to stimuli and manipulating objects for short periods of time. This distributed neural architecture means an octopus may experience the world very differently from humans, with multiple semi-independent control centers working together. Studying these animals challenges human-centered ideas about consciousness. It suggests that intelligence and awareness may emerge in many different biological forms. Certain birds show problem-solving abilities comparable to young children. Species such as crows, ravens, and parrots have demonstrated remarkable cognitive skills, despite having much smaller brains than mammals. New Caledonian crows have been observed bending pieces of wire into hooks to retrieve food from difficult locations, a behavior that requires planning and foresight. African gray parrots have learned to recognize numbers, colors, and even the concept of zero. These abilities indicate a level of mental flexibility once believed to exist only in humans and great apes. Birds achieve this through a highly efficient brain structure called the pallium, where neurons are densely packed and intricately connected. Their intelligence shows that advanced cognition can evolve in many different neural architectures. Modern machines can simulate human conversation without possessing awareness. Artificial intelligence systems can generate convincing speech, answer complex questions, and even produce creative writing. These systems operate by analyzing patterns in enormous data sets and predicting which words are most likely to follow one another. Although their responses may sound thoughtful or emotional, they do not involve subjective experience. There is no inner awareness behind the words. This distinction lies at the heart of debates about machine consciousness. A machine may imitate intelligent behavior extremely well, but imitation alone does not necessarily imply understanding. Without subjective experience, it may simply be manipulating symbols according to learned patterns. The Chinese room thought experiment questions whether computers can truly think. Philosopher John Searle proposed a famous thought experiment known as the Chinese room argument. Imagine a person who does not understand Chinese sitting inside a room with a detailed rule book for manipulating Chinese characters. When messages written in Chinese are passed into the room, the person follows the rule book and produces appropriate responses. To someone outside the room, the answers appear fluent and intelligent. However, the person inside still does not understand Chinese at all. They are simply following instructions. Searle used this example to argue that computers might operate in a similar way, processing symbols without genuine understanding. The argument remains influential in philosophy and continues to shape discussions about artificial intelligence and consciousness. The hard problem of consciousness remains one of the deepest mysteries in science. Philosopher David Chalmers introduced the term the hard problem to describe the challenge of explaining why physical processes in the brain give rise to subjective experience. Scientists can identify which brain areas activate when we see colors, hear music, or feel emotions. Yet even with this knowledge, another question remains unanswered. Why do these processes feel like anything at all from the inside? Why does electrical activity in neurons produce the sensation of red, the taste of sweetness, or the feeling of sadness? This gap between measurable brain activity and personal experience has resisted decades of research. Some researchers believe the solution will eventually come from more advanced neuroscience. Others suspect it may require a completely new way of understanding reality itself. Until that explanation is found, the hard problem remains one of the most profound puzzles in modern science. Some philosophical theories propose that consciousness exists in all matter. One such idea is known as panpsychism. According to this theory, consciousness is not something that suddenly appears when brains become complex enough. Instead, it may be a fundamental property of the universe, present in some extremely basic form within all matter. In this view, even particles or simple systems might possess tiny fragments of awareness. Supporters of panpsychism argue that this idea could help explain how subjective experience arises in the first place. Critics, however, point out that such theories are difficult to test and may stretch the concept of consciousness too far. Even so, the idea has gained renewed attention among some philosophers and scientists searching for new ways to bridge the gap between physical processes and subjective experience. Quantum theories of consciousness suggest that subatomic processes may influence awareness. Some researchers have proposed that quantum mechanics, the physics governing extremely small particles, could play a role in consciousness. One theory, known as orchestrated objective reduction, proposes that quantum processes occurring within tiny structures inside neurons called microtubules might contribute to awareness. According to this hypothesis, these microscopic events could influence large-scale brain activity in ways that generate conscious experience. However, the theory remains controversial. The brain's warm and complex biological environment is generally thought to disrupt delicate quantum states before they could influence neural processes. While evidence for quantum consciousness remains limited, exploring such possibilities keeps open the idea that awareness might be connected to the most fundamental physical laws of the universe. Many neuroscientists consider quantum explanations of consciousness unlikely. Most brain researchers believe that classical biological processes are sufficient to explain how the brain functions. Quantum effects have been observed in certain biological systems, such as photosynthesis, but applying those principles to complex mental activity is considered a much larger leap. Current models of neuroscience can explain perception, learning, and decision-making through networks of neurons communicating through electrochemical signals. Nevertheless, the mystery of consciousness remains so deep that even unlikely theories continue to attract interest. Until a complete explanation emerges, the debate continues. The brain produces different types of electrical waves linked to mental states. Electrical activity within the brain occurs in rhythmic patterns known as brain waves. These waves are classified by their frequency, measured in cycles per second, called hertz. Each type of brain wave is associated with particular mental states. Faster waves tend to appear during active thinking or intense focus, while slower waves dominate during relaxation and deep sleep. Scientists measure these patterns using electroencephalography, or EEG, which records tiny voltage changes from electrodes placed on the scalp. These recordings reveal that the brain is constantly shifting between different rhythms depending on what we are doing, feeling, or thinking. This dynamic pattern suggests that consciousness itself may not be a single state, but a constantly changing pattern of neural activity. Gamma waves are associated with complex thinking and memory processing. Gamma waves are the fastest known brain waves, cycling more than 30 times per second. They are often linked to high-level cognitive functions such as problem-solving, memory recall, and the integration of information from multiple senses. When you suddenly understand a complex idea or experience an aha moment, gamma activity often increases. Researchers believe these waves help synchronize different regions of the brain, allowing separate pieces of information to combine into a unified perception. Interestingly, experienced meditators sometimes display unusually strong gamma activity, suggesting that mental training can influence these patterns. Although gamma waves alone do not determine intelligence, they appear to play an important role in the flexible and interconnected nature of conscious thought. Alpha waves appear during relaxed but wakeful states. Alpha waves occur at a slower rhythm, typically between 8 and 12 cycles per second. They are most prominent when a person is awake yet calm, such as during quiet reflection, meditation, or just before falling asleep. When you close your eyes and reduce incoming visual information, alpha activity often increases. Scientists believe these waves help filter out irrelevant sensory input, allowing the mind to focus inward. Alpha waves have also been linked to creativity, relaxation, and improved learning. Practices such as meditation, breathing exercises, and mindfulness often enhance alpha activity, which may explain why these techniques promote mental calmness. Theta waves are strongly connected to dreaming and imagination. Theta waves oscillate even more slowly, typically between 4 and 8 cycles per second. They appear most often during light sleep, dreaming, and deep meditative states. During theta activity, the mind often becomes more imaginative and associative. Memories, images, and ideas may blend together in unusual ways, which is why theta states are frequently linked to creativity. Some people intentionally try to enter theta states through meditation or hypnosis to encourage new insights or creative thinking. Theta activity may also play an important role in processing emotional experiences and transferring memories into long-term storage. Delta waves dominate during the deepest stages of sleep. Delta waves are the slowest brain waves, cycling fewer than 4 times per second. They are most common during the deepest phases of non-REM sleep, when the body focuses on restoration and repair. During this stage, tissues regenerate, the immune system strengthens, and certain types of memories are consolidated. Conscious awareness is extremely limited during deep delta sleep, yet the brain remains active in maintaining essential bodily functions. High levels of delta activity are also common in infants and young children whose brains are still developing rapidly. For adults, spending enough time in deep sleep is essential for physical recovery and mental health. The brain produces brief electrical ripples while forming memories. When the brain encodes new experiences into memory, it generates short bursts of high-frequency electrical activity called ripples. These events occur mainly in the hippocampus, a region crucial for memory formation. During sleep, especially slow-wave sleep, these ripples replay patterns of activity that occurred during waking experiences. This replay strengthens neural connections and helps transfer memories into long-term storage. Scientists believe these electrical ripples allow distant brain regions to synchronize with one another, reinforcing the networks that hold memories. Experiments with animals have shown that disrupting these ripples can impair learning, while enhancing them may improve memory retention. Hallucinations can occur when the brain is deprived of oxygen. When the brain receives insufficient oxygen, a condition called hypoxia occurs. Under these conditions, perception can change dramatically. People may see bright flashes of light, experience tunnel vision, or even encounter complex hallucinations. These effects can happen during high-altitude climbing, deep diving accidents, or medical emergencies. Oxygen deprivation disrupts normal neural activity, particularly in areas responsible for vision and spatial awareness. These unusual perceptions are often accompanied by dizziness, confusion, or a feeling of detachment from reality. Although dangerous, studying these states helps scientists understand how fragile conscious perception can be when the brain's basic needs are not met. Astronauts have reported unusual sensory experiences while in space. Life aboard the International Space Station places the human body in conditions unlike anything on Earth. Some astronauts have described vivid dreams, flashes of light when their eyes are closed, and occasionally hearing phantom sounds. Some of these effects may be caused by cosmic rays striking the retina. Others may result from disrupted sleep cycles or the psychological impact of long periods of isolation. Microgravity also changes how fluids move through the body, potentially affecting brain function. These unusual experiences give scientists rare insight into how consciousness adapts when humans leave the familiar environment of Earth. Microdosing psychedelic substances may subtly change cognitive patterns. Microdosing refers to taking very small amounts of psychedelic compounds such as LSD or psilocybin. These doses are typically far below the level required to produce strong hallucinations. People who practice microdosing sometimes report improved mood, increased focus, and enhanced creativity. Early research suggests that microdosing may slightly alter the connectivity between brain networks, potentially encouraging more flexible thinking patterns. However, many of the reported benefits remain anecdotal, and placebo effects may play a significant role. Controlled scientific studies are still ongoing to determine whether these effects are real and how they might work. Some people experience flow states, where time seems to vanish. A flow state occurs when a person becomes completely absorbed in an activity. During flow, attention becomes intensely focused, self-awareness fades, and the sense of time often disappears. Athletes, musicians, artists, and programmers frequently report entering flow while performing challenging but enjoyable tasks. Brain studies suggest that flow involves reduced activity in the default mode network, the brain system associated with self-reflection. At the same time, coordination between attention and motor systems increases. This creates a feeling of effortless concentration and deep engagement. Flow states demonstrate how consciousness can become so focused that the rest of the world seems to dissolve temporarily. Certain migraines can dramatically distort perception. Some individuals who experience migraines develop sensory disturbances called auras before the headache begins. These auras may include flashing lights, zigzag patterns, blind spots, or unusual distortions in visual perception. In rare cases, objects may appear unusually large or small. Straight lines may seem bent, and familiar faces may appear distorted. Scientists believe these effects result from waves of electrical activity spreading across the visual cortex. Although unsettling, these disturbances usually fade within an hour. Studying migraine auras provides insight into how delicate the balance of neural activity is that allows us to perceive the world accurately. Déjà vu may be the result of a small glitch in the brain's memory system. Déjà vu is the strange sensation that a current moment has already happened before. Many people experience it at least once in their lives. One leading theory suggests that déjà vu occurs when incoming sensory information is briefly misrouted inside the brain. Instead of first reaching conscious awareness, the signal may pass through memory processing systems. As a result, when the experience finally reaches conscious perception, it feels as if it is already familiar. Another theory proposes that déjà vu happens when two parallel processing systems in the brain fall slightly out of sync. When this happens, the brain mistakenly labels the present moment as a memory. Most episodes of déjà vu last only a few seconds and are harmless. However, in people with certain forms of epilepsy, the experience can occur more frequently. Because of this, scientists sometimes study déjà vu in clinical settings to better understand how memory and awareness interact. Jamais vu creates the opposite experience, when something familiar suddenly feels unfamiliar. Jamais vu is the strange counterpart to déjà vu. Instead of a new situation feeling strangely familiar, something well-known suddenly feels strange or unfamiliar. A person may stare at a common word until it seems meaningless, or walk through a familiar room and briefly feel as though they have never seen it before. Scientists believe this happens when the brain's recognition systems momentarily fail to generate the normal sense of familiarity. Jamais vu can sometimes be triggered intentionally through repetition, such as repeating a word until it loses its meaning. In other cases, it may appear during fatigue or certain neurological conditions. Although usually brief, the experience reveals how actively the brain constructs the feeling of familiarity in everyday perception. The brain reconstructs the present moment from slightly delayed signals. Light takes time to reach the eyes, sound requires time to reach the ears, and sensory signals require additional time to travel through the nervous system and be processed by the brain. Yet we experience the world as if everything happens instantly. To create this seamless experience, the brain continuously integrates signals from multiple senses and assembles them into a unified present moment. If these signals arrive too far apart in time, the illusion of simultaneity breaks down and events no longer feel synchronized. Experiments using delayed audio or visual signals demonstrate how fragile this sense of now can be. What we experience as the present is actually a carefully reconstructed version of reality created by the brain. Blending illusions show how the brain smooths over gaps in perception. Our senses do not capture every detail of the world. Instead, the brain fills in missing information to create a continuous experience. In certain visual illusions, moving objects may briefly disappear from sight, yet we still perceive smooth motion because the brain blends information from the past and predicted future positions. This process helps maintain stability in a constantly changing environment. However, it also means that what we consciously perceive is not always perfectly accurate. Much of perception involves prediction. The brain uses prior knowledge to create the most likely interpretation of incoming sensory signals. Near-death experiences sometimes include feelings of peace and detachment. Individuals who come close to death occasionally report powerful experiences, such as floating above their bodies, traveling through tunnels of light, or feeling a deep sense of calm. These experiences may result from dramatic changes in brain chemistry and neural activity during extreme stress or oxygen deprivation. Some researchers believe that bursts of electrical activity in dying brain cells may contribute to these vivid perceptions. Others suggest that protective neurochemical responses may produce feelings of calm or detachment. Although interpretations vary widely, the consistency of many near-death reports across cultures makes them a fascinating area of scientific study. Some people report life reviews that unfold in seconds during moments of extreme danger. In certain life-threatening situations, individuals describe seeing their entire life flash before their eyes. These experiences may involve rapid sequences of memories, often accompanied by intense emotional detail. Scientists believe this phenomenon may occur when stress hormones trigger rapid activation of memory networks in the brain. This surge of activity could allow large numbers of memories to be accessed in a very short time. Although the exact mechanism remains uncertain, such experiences suggest that the brain can retrieve enormous amounts of stored information almost instantly under certain conditions. The sense of self may be a continuous illusion created by the brain. Many neuroscientists believe that the feeling of having a stable self is actually a model constantly generated by the brain. This internal model integrates sensory information, memories, and goals to create the impression of a continuous identity. However, this sense of self can be disrupted by injuries, neurological conditions, or certain drugs. Disorders such as depersonalization can cause individuals to feel detached from their own thoughts or bodies. These cases suggest that the self is not a fixed entity, but a dynamic process maintained by the brain. Even very simple organisms display forms of decision-making. Single-celled organisms, such as amoebas and bacteria, do not possess nervous systems, yet they can move toward nutrients, avoid harmful substances, and adapt to environmental changes. These behaviors are guided by chemical signaling rather than conscious thought. Still, they show that basic forms of decision-making can exist even without a brain. Studying these organisms provides clues about the evolutionary origins of more complex forms of awareness. Slime molds can solve simple problems despite lacking a brain. Slime molds are single-celled organisms that grow into branching networks. In laboratory experiments, scientists have placed slime molds inside maze-like structures with food sources at different exits. Over time, the slime mold retracts from dead ends and forms the most efficient path between food sources. Although this process is driven by chemical feedback rather than neurons, the result resembles problem-solving. These organisms demonstrate that surprisingly complex behaviors can arise even in systems without nervous tissue. Your brain continues working during light stages of sleep. Light sleep occurs during the early phases of the sleep cycle. During these stages, the brain does not completely shut down awareness. Instead, it continues processing external sounds, bodily sensations, and fragments of conversation. This is why people may wake easily if someone calls their name. Brain recordings during light sleep reveal slower waves mixed with brief bursts of faster activity, known as sleep spindles. These spindles are believed to help filter out unimportant sensory information, while still allowing the brain to respond to significant signals, such as alarms or crying infants. Severe sleep deprivation can produce hallucinations. Staying awake for long periods does more than create fatigue. It can significantly disrupt perception and cognition. After roughly 72 hours without sleep, many individuals begin experiencing visual distortions, moving shadows, or even complex hallucinations. These effects occur because the brain struggles to maintain stable sensory processing without the restorative processes of sleep. In extreme cases, prolonged sleep deprivation can lead to paranoia and symptoms similar to psychosis. Fortunately, these effects usually disappear once normal sleep patterns are restored. Long-term sleep loss can mimic symptoms of mental illness. Chronic sleep deprivation over weeks or months can lead to serious emotional and cognitive changes. People may experience confusion, memory problems, anxiety, and distorted perception of reality. The prefrontal cortex, responsible for planning and impulse control, is particularly vulnerable to sleep loss. Over time, prolonged sleep deprivation can produce symptoms resembling psychiatric disorders, including delusions and hallucinations. This connection highlights the crucial role sleep plays in maintaining stable consciousness. Insomnia can disrupt emotional regulation in the brain. Chronic insomnia does more than cause tiredness. It can fundamentally alter how the brain processes emotional experiences. Studies show that individuals with long-term insomnia often have increased activity in the amygdala, the brain's threat detection center. At the same time, communication between the amygdala and the prefrontal cortex becomes weaker. This imbalance can make everyday stress feel more intense and difficult to manage. Over time, sleep disruption can increase the risk of mood disorders such as anxiety and depression. The brain performs deep cleaning during sleep. During the deepest stages of non-REM sleep, a system known as the glymphatic system becomes highly active. This system flushes metabolic waste products from brain tissue using cerebrospinal fluid. Harmful substances such as beta-amyloid proteins, which are associated with Alzheimer's disease, are removed more efficiently during sleep than during wakefulness. This nightly cleaning process is one reason why deep sleep is essential for long-term brain health. REM sleep may help process emotional experiences. Rapid eye movement sleep is the stage most strongly associated with vivid dreams. During this stage, activity in emotional brain regions remains high, while stress chemicals such as norepinephrine decrease. This unusual combination may allow the brain to revisit emotional memories in a safer context. Some researchers describe REM sleep as a form of overnight emotional therapy, helping the brain integrate difficult experiences without overwhelming waking consciousness. Dream content can sometimes be influenced by the outside environment. Even while dreaming, the brain does not completely shut itself off from external sensory information. Researchers have discovered that sounds, lights, and even smells introduced during sleep can subtly influence the direction and content of dreams. For example, the sound of running water played near a sleeping person might appear in a dream as a flowing river or rain. Likewise, pleasant scents such as roses can lead to more positive dream imagery, while unpleasant smells may produce darker or more unsettling dream scenes. This does not happen every time, but it demonstrates that dreams are not entirely sealed off from the outside world. Instead, dreaming appears to be a mixture of internal memory processing and subtle environmental input. Certain smells or sounds presented during sleep can shift the emotional tone of dreams. Experiments involving scent cues, such as peppermint, roses, or smoke, have shown that odors can affect dream content without waking the sleeper. Pleasant scents tend to produce more positive dream experiences, while unpleasant ones can increase negative emotional tone. Gentle music or environmental sounds can also guide dream themes. sometimes leading to dreams that incorporate the sound source. Although these techniques remain experimental, they suggest the possibility of influencing dreams for therapeutic purposes. Researchers have begun exploring whether such methods might help reduce nightmares or assist with emotional processing during sleep. People in REM sleep can sometimes respond to simple questions. Recent studies have demonstrated that lucid dreamers can communicate with researchers while still inside a dream. In these experiments, participants were trained to move their eyes in specific patterns or produce small facial muscle movements in response to questions asked by scientists. Because these movements can be detected by sleep monitoring equipment, researchers were able to receive answers while the dream was still occurring. This remarkable discovery provides a direct way to study dream consciousness in real time rather than relying solely on reports after waking. Sleep talking can reveal thoughts that the sleeper never intended to share. Sleep talking, also called somniloquy, can occur during almost any stage of sleep. A person might whisper, mumble, speak full sentences, or even carry out short conversations while still asleep. Most individuals have no memory of speaking during the night. Because sleep talking occurs without the usual self-control present during waking consciousness, it has fascinated researchers interested in the unconscious mind. However, interpreting sleep speech is difficult. The words spoken may be fragments of dreams, emotional echoes from waking life, or simply random neural activity. Strokes can cause sudden shifts in awareness and consciousness. A stroke occurs when blood flow to a region of the brain is interrupted, depriving neurons of oxygen and nutrients. When brain areas involved in awareness are affected, the results can include sudden confusion, loss of responsiveness, or even coma. In milder cases, individuals may experience temporary disorientation or memory lapses. The effects depend heavily on which region of the brain is damaged. Strokes affecting the brainstem may impair wakefulness itself, while strokes in frontal or parietal areas can alter perception, attention, or self-awareness. Recovery varies widely. Some people regain normal awareness within hours, while others require long rehabilitation. Alien hand syndrome can cause a limb to move without conscious intention. Alien hand syndrome is a rare neurological condition in which one hand appears to act independently of the person's conscious will. The hand may grasp objects, unbutton clothing, or interfere with actions performed by the other hand. Although the individual can see and feel the movements, they do not experience a sense of controlling them. This condition is often associated with damage to brain regions that coordinate intention and motor control, particularly the corpus callosum or frontal lobes. The movements themselves are purposeful rather than random, which makes the experience particularly unsettling for those affected. Some rare psychiatric conditions cause individuals to believe they are dead. Cotard syndrome is an unusual disorder in which a person believes they are dead, do not exist, or have lost their internal organs. This condition often appears alongside severe depression, psychosis, or neurological damage. Patients may insist that their body is decaying or that they no longer need food or water because they are already dead. Brain imaging studies suggest abnormalities in networks responsible for self-awareness and emotional processing. Although rare, this disorder demonstrates how strongly our sense of being alive depends on specific brain systems functioning normally. Cotard's delusion represents one of the most extreme disturbances of self-awareness. Named after the French neurologist Jules Cotard, this condition can cause people to believe their organs have disappeared, that their blood has dried up, or that the world itself has ceased to exist. The disorder is thought to result from disrupted connections between brain regions responsible for recognizing sensory information and those that assign emotional meaning to it. When this connection fails, the brain may perceive sensory signals but fail to generate the normal feeling of presence or vitality. For scientists studying consciousness, Cotard syndrome highlights how essential emotional interpretation is for maintaining the sense of self. Capgras delusion can make familiar people seem like imposters. In Capgras syndrome, individuals become convinced that someone close to them has been replaced by an identical-looking imposter. The affected person may recognize the face of a spouse, friend, or family member, yet feel that something is wrong. Researchers believe this condition occurs when facial recognition systems in the brain remain intact, but their connection to emotional response centers is disrupted. As a result, the face is recognized visually, but fails to produce the normal feeling of familiarity. The brain attempts to explain this mismatch by concluding that the person must be a duplicate. Certain brain injuries can erase the ability to recognize faces. Prosopagnosia, also known as face blindness, is a neurological condition in which individuals lose the ability to recognize familiar faces. People with this condition can still see faces clearly and describe features in detail, yet they cannot identify who the face belongs to. Even close family members may appear unfamiliar. The condition typically results from damage to a brain region called the fusiform gyrus, which plays a key role in facial recognition. Many individuals with prosopagnosia learn to rely on alternative cues such as voice, hairstyle, or body language to identify people. Interestingly, some people with face blindness still recognize faces unconsciously. Studies have shown that certain individuals with prosopagnosia display physiological reactions when shown familiar faces. Their heart rate or skin conductance may change, indicating that some part of the brain still recognizes the person. However, this recognition does not reach conscious awareness. This phenomenon illustrates that perception and conscious recognition can operate separately in the brain. Some individuals cannot form mental images at all. A condition known as aphantasia prevents people from visualizing images in their minds. Individuals with aphantasia can recall facts, recognize faces, and describe objects, but when asked to imagine something, such as a beach or an apple, they do not see a mental picture. Instead, they may think in concepts or verbal descriptions. The discovery of aphantasia has challenged long-held assumptions about imagination, showing that vivid internal imagery is not universal. Others experience the opposite condition known as hyperphantasia. Hyperphantasia refers to extremely vivid mental imagery. People with this trait can create highly detailed visual scenes in their minds, sometimes as clear as actual perception. This ability can support creativity in fields such as art, design, and storytelling. However, the intensity of such imagery can also make it difficult to separate imagination from real sensory input. Short-term memory can hold only a limited number of items at once. Psychologist George Miller famously proposed that short-term memory can typically hold about 7 pieces of information at a time, give or take 2. This capacity varies depending on the type of information and the strategies used to remember it. One technique, known as chunking, allows people to group information into meaningful units, making it easier to store temporarily. Working memory allows the brain to manipulate information actively. Unlike simple short-term storage, working memory acts more like a mental workspace. It allows us to hold information while performing operations on it. Activities such as solving math problems, following instructions, or planning decisions rely heavily on working memory. This system depends on cooperation between the prefrontal cortex and other brain regions involved in attention and spatial processing. Long-term memories are stored across many different regions of the brain. Unlike a computer, which saves information in a single location, the human brain distributes memories across a wide network of areas. The visual parts of an experience may be stored in the visual cortex, sounds in the auditory cortex, and emotional elements in structures such as the amygdala. The hippocampus acts as an organizer that helps link these separate fragments together. When you recall a memory, the brain reconstructs the event by reactivating many of these distributed areas at once. Because of this, remembering is not simply retrieving a stored file. It is more like rebuilding a scene from scattered pieces, which means each act of recall can slightly reshape the memory itself. Emotional experiences tend to be remembered more strongly than neutral ones. When an event carries emotional significance, the amygdala signals the hippocampus to strengthen the encoding of that memory. From an evolutionary perspective, this makes sense. Remembering important or dangerous events helps organisms avoid threats and repeat beneficial behaviors. Emotional memories often feel vivid and detailed, but they are not necessarily more accurate. In fact, strong emotions can sometimes distort certain details while amplifying others. Even many years later, recalling such experiences can still trigger powerful feelings. False memories can sometimes be created through suggestion. Human memory is not a perfect recording device. It is a flexible system that can be influenced by outside information. In psychological studies, participants have occasionally been persuaded to remember events that never actually occurred. Repeated suggestions or exposure to misleading details can gradually reshape a person's recollection of the past. These implanted memories can feel just as real as genuine ones, including emotional reactions. This phenomenon has important implications for eyewitness testimony and highlights how vulnerable memory can be to subtle influences. Group discussions can alter how people remember shared events. When individuals recall an experience together, their memories can gradually shift to align with the group's version of events. Psychologists call this phenomenon memory conformity. Hearing someone else confidently describe a detail may lead others to incorporate that detail into their own recollection, even if it was not present originally. Over time, a collective memory may emerge that differs significantly from what actually occurred. This shows that memory is not only an individual process, but also a social one. Future technologies may restore lost memories using brain implants. Scientists are currently developing neural prosthetic devices designed to mimic the electrical patterns involved in memory formation. By recording activity in the hippocampus and reproducing those patterns artificially, researchers have already managed to enhance memory performance in some experimental studies. The long-term goal is to help people who suffer from memory loss caused by injury or neurodegenerative diseases. Although still experimental, These technologies hint at a future in which damaged memory circuits might be repaired or supported with artificial systems. Digital technology has already expanded the boundaries of human memory. Smartphones, computers, and the Internet function as external memory storage systems. Instead of remembering every piece of information ourselves, we often remember where to find it. Psychologists sometimes call this the Google effect. Knowing that information is easily accessible online can reduce the need to store it internally. This shift allows the brain to allocate attention to other tasks. But it also means our relationship with knowledge is changing. Memory is becoming increasingly distributed between human minds and digital systems. Language can shape how people experience and organize their thoughts. Different languages describe the world in different ways, influencing how speakers perceive time, space, and relationships. Some languages rely heavily on absolute directions, such as north, south, east, and west, rather than relative directions like left or right. Speakers of these languages often develop an unusually strong sense of orientation. Other languages contain more nuanced color terms, allowing speakers to distinguish shades that might otherwise seem identical. This idea, sometimes associated with the Sapir-Whorf hypothesis, suggests that language may shape aspects of conscious thought. People who speak multiple languages sometimes shift mental frameworks when switching languages. Multilingual individuals often report feeling slightly different depending on which language they are using. They may sound more formal, emotional, or direct depending on the cultural context associated with that language. Research suggests that switching languages can influence attention patterns, decision-making styles, and emotional responses. This phenomenon, sometimes called cultural frame switching, shows how flexible the human mind can be. Bilingual individuals may experience delayed symptoms of dementia. Some studies have found that people who regularly use 2 or more languages develop symptoms of dementia several years later than those who speak only one language. The mental effort involved in switching between languages strengthens executive control systems in the brain. This process builds what researchers call cognitive reserve. Although bilingualism does not prevent dementia entirely, it may help the brain compensate for damage for a longer period of time. Inner speech activates many of the same brain regions used in spoken language. When you talk to yourself silently in your mind, areas involved in speech production and auditory processing often become active. This inner dialogue can help with planning, problem-solving, and emotional regulation. For many people, inner speech functions almost like a private narrator that organizes thoughts and rehearses ideas before they are spoken aloud. However, not everyone experiences a constant inner voice. Some individuals report having very little internal verbal dialogue. Their thoughts may appear more as images, sensations, or abstract concepts rather than words. This difference does not appear to affect intelligence. Instead, it highlights the diversity of conscious experience among individuals. At the other extreme, some people experience nearly constant internal narration. Their thoughts may unfold as an ongoing stream of commentary about events, decisions, and imagined conversations. While this inner dialogue can be useful for organizing ideas, it can also contribute to rumination or anxiety if it becomes excessive. Brain imaging studies show that such internal chatter is associated with activity in the brain's default mode network. meditation can produce measurable physical changes in the brain. Long-term meditation practice has been linked to increased thickness in certain brain regions associated with attention, emotional regulation, and sensory awareness. Areas such as the prefrontal cortex and insula often show structural changes in experienced meditators. These findings demonstrate the brain's capacity for neuroplasticity, meaning that repeated mental training can reshape neural structures over time. Mindfulness practices can reduce activity in the default mode network. The default mode network becomes active when the mind wanders or engages in self-focused thinking. Excessive activity in this network has been associated with rumination and certain mood disorders. Meditation and mindfulness practices appear to quiet this network, shifting attention toward present moment awareness. Many practitioners describe this shift as a calmer, more focused state of consciousness. Hypnosis can alter how the brain interprets sensory signals. Under hypnosis, some individuals experience dramatic changes in perception. Colors may appear different, sounds may fade into the background, and pain sensitivity can decrease significantly. Brain imaging studies show altered patterns of activity in sensory processing areas during hypnosis. These changes suggest that suggestion and focused attention can reshape how the brain interprets incoming information. Placebo responses demonstrate how belief can influence perception and physiology. When people expect a treatment to work, their brains sometimes produce measurable physiological changes. For instance, believing that one has taken a pain-relieving medication can trigger the release of natural pain-reducing chemicals. This effect shows that expectation alone can influence both the experience of symptoms and certain bodily responses. Some philosophical theories suggest that consciousness may be a fundamental property of reality. Instead of emerging only from complex brains, awareness might exist in a very basic form throughout the universe. This idea remains controversial, but it represents one attempt to explain why subjective experience exists at all. Despite centuries of thought and decades of scientific research, the mystery of consciousness remains unsolved. Scientists can map neural activity associated with perception, emotion, and memory. Yet the connection between these physical processes and the rich inner world of experience remains elusive. Consciousness research spans many fields, including neuroscience, psychology, philosophy, physics, and artificial intelligence. Each discipline offers pieces of the puzzle, but the complete picture is still unknown. And so our quiet journey through the landscapes of awareness slowly comes to an end. We have wandered from the fragile moment when a thought appears in the brain to the vast questions about whether consciousness might be woven into the structure of the universe itself. We explored the edges where memory fades, where identity dissolves, and where awareness can briefly disappear before returning again. Even now, as you lie here listening, your mind continues its gentle work, breathing quietly, sensing the world around you, gradually releasing the thoughts of the day. Your awareness may already be softening, the details fading at the edges like distant dreams. Perhaps when morning arrives, you will remember a few of these ideas, or perhaps they will drift away, leaving behind only the quiet sense that you traveled through something vast and mysterious. For now, there is nothing you need to solve, nothing you need to hold on to. Let your thoughts slow, like leaves settling on calm water. The day is finished. If your eyes are still open, Another video is waiting for you, but if they are already closed, simply remain where you are and allow sleep to carry you the rest of the way.